All right, recording, rolling. It is Thursday, November 16th. We're going to do a review of energy and momentum today. This is what we've been doing the last 4 weeks in this class, right? So energy took a couple of weeks, momentum took a couple of weeks. This is all for this in-class quiz tomorrow. In-class quiz tomorrow, there's going to be 10 of these questions and 10 of these questions, total of 20 questions. And we got classes that are, like a little under 40 minutes. So I guess that gives you about little under 2 minutes per question. But I think that works for this type quiz, right? Right. So remember, this quiz is common to all physics classes. So like regular, honors, AP, all take the same thing, and on all different teachers. We're all given the same quiz. It's a thing we're doing. Right? And so we're coming up to Thanksgiving break. Reminder before you guys leave for Thanksgiving break. Remember the interim entered yesterday. I'm gonna put grades in here in a couple of days. Okay. Make sure you've at least turned in these couple of things is well, it's a good starter checklist, right? So chapter 9 puzzles for momentum, right? We've covered all these in class. This half page. I'm treating this like 2 homeworks for this section, 2 homeworks. Okay. A lot of you guys have already turned these in. If you want to hold on to them for one more day to study for this quiz tomorrow, then that might be a good idea. But just make sure that you turn these into the grade tray before you leave for Thanksgiving. Okay. So yeah, let's review. I think a good way to do this review is to go through these posters, right? And there's a few new posters because then pick up some updates, right? And then throw some example questions at you guys. Right? And if you have any questions, let me know as we go along. I think it should be plenty comprehensive enough to get you guys ready for tomorrow. Camera adjustment here. Right. Right. So maybe beginning here. Energy and momentum. Right, so I got some green boxes and I got a couple of blue boxes down at the bottom. Right, so all the green boxes are energy related. Right, so energy, see measured in joules. Work is a transfer of energy, so also measured in joules. Okay, there is see potential energy, gravitational, or stored in a spring. Right, so you like stretch a spring, take some work to stretch it, and there's some energy stored in it. Right, or right, I show you guys this idea too. Like if you press a pen down. Press the cartridge into the spring, it's like spring-loaded pow, right? Some energy stored in it. Right? There could be energy in motion, right? Called kinetic energy. Right? Rotational kinetic, don't quite worry about that yet, but when you guys come back from Thanksgiving break, then we'll get into rotational dynamics. So this one will come up, right? Like a tire rolling downhill or something like that, right? Or a marble rolling downhill, right? But there's also, okay, now those are all in joules, joules, like different perspectives on energy transfer, right? Also in that section was power. And that was measured in, what does capital W represent in this context right here? Watts, right? Like you look on a light bulb, it says 40 watts. That's like joules per second, right? Then these past couple weeks, we've been doing momentum, right? Just like mass times velocity, that's kilogram meter per second, right? Or a transfer of momentum, like a change of momentum, delta P, change of momentum, transfer of momentum. That's called impulse, fancy word for that. A lot of times quantified in Newton seconds, like force times time. Hey, guys, are these 2 units equivalent? Kilogram meter per second and Newton's time seconds. Is that the exact same thing? That is the exact same thing, right? They both something to do with momentum transfer. Right, so you got that. Right, here's a poster just for joules and watts. There we go, right? Energy or work could be measured in joules. What is 1 joule, right? Well, it breaks down into 1 Newton times 1 meter, which even if you didn't quite know that, you could figure it out because coming up pretty soon. You guys remember work is force times distance, right? Oh, there's a force, there's a distance. Boom. Right? Okay, and then furthermore, that you could break that down because newtons is a composite unit. So here it is in terms of base SI units. And then power, right? Measured in watts. That's like a rate of energy. Oh, look at that. 1 watt is 1 joule per second, right? Joules per second. Right. So if you have a 40-watt light bulb, it's pulling 40 joules per second, either off the grid or from a battery. Right? Okay, and then furthermore, that breaks down into these units. Those are all equivalent. Right. Oh, look at these two. Right. Compare them. Right. Look pretty same, and then seconds squared, seconds cubed. Right. Right. Oh, right. So we're actually I feel like I meant to have this paper shoveled up close to the front. Right. Here we go. Right. So here's forms of mechanical energy. Right. Work. Now this capital W is as a variable, not as a unit, but as a variable to represent work. Right. So careful with that. As a variable, capital W in physics could be work. As a unit, it could represent watts. That's a completely different context, completely different meaning. So this W and that W are not the same thing, right? So just context if you're ever reading a physics book, right? So force times distance, right? Here, my more specific version of this is that's a dot product. So you only multiply the parallel components. Okay? So if I'm lifting something, right, it takes some force to lift it. Right? And if I lift it higher, 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 I'm doing work lifting it. But if I carry this across the room horizontally, I'm not actually doing any work. Right? It's like some technical reasons why that is mattering, right? But for here, we've got force times distance, but we've got a dot product. So if there's an angle between the force and the distance, just multiply by the cosine of the angle between. If you're carrying something up the stairs, then lifting it, yeah, you're doing work. But carrying it across doesn't actually require any energy to do that. Right? If you're pushing a shopping cart forward, like down and forward, but the shopping cart only moves forward, right? Then remember the downward component that you push doesn't actually do any energy transfer, right? But the parallel component to its motion does, right? So we get a cosine out of that, right? Now, careful. Sometimes you guys ran into this too. You guys remember the question? There was like somebody taking the world's longest escalator in Hong Kong. You guys remember that? The angle they ended up giving you was actually sort of like the opposite angle. Like think of it kind of like this angle right here is what they gave you. It's like so many degrees, right? So that turned this from a cosine into a sine. So careful about that. If they give you the wrong angle, this might be a sine instead of a cosine. But if it's the angle between the vectors, it's always cosine. Okay? I think actually what I'm telling you guys right now, I think is a little bit more technical than anything that would quite be asked on the quiz tomorrow. But yeah, it's always got a little bit of extra stuff, right? Okay. So force times distance, right? And if you lift a weight a certain height, that could be a version of this, and that leads exactly to this next one. Bam. Right? So if I lift a certain weight, a certain height, say it's okay, 10 newtons to lift this, and I lift it like 1 meter, 10 newtons, right? Mg times 1 meter lifting. That's like 10 joules it takes to lift it. Right? And if I stack this on the edge of the table, that's also 10 joules of potential energy that it has, MGH, right? MGH. Okay. Mostly focus on these gold boxes, not so much the greens, especially for tomorrow quiz, don't worry so much, but just to remind you guys, right, there's actually 2 perspectives on potential energy. Now, the more universal perspective, we actually did use this at least once before to solve for escape speed. If you send a rocket all the way to Mars, how fast you have to go to escape Earth's gravity. And the difference is, that gravity field, like we've been treating this like 9.8 meters per second squared, so 10 meters per second squared, is not constant when you get too far away from Earth, or if you tunnel too deep for that matter, right? You can show that a change in this more general form just simplifies to MGH, right? But for tomorrow, for the quiz, all you care about is like MGH, right? Energy stored in a spring, 1/2 kx squared. A lot of students confuse this with Hooke's law, F equals kx. That's 2 different concepts. So F equals kx is like, well, it takes some force to stretch the spring or compress it in the case of like pressing my pen. Takes some force. Takes some force to stretch. Right? The work it takes to stretch is 1/2 kx squared. Right? And that's also the energy stored in the spring. So if I go, how? Right? In this case, how? Where'd that energy come from? How? Right? Well, it's stored in the spring, 1/2 kx squared. K is how stiff the spring is. Now there is a graph form of those two. Let me whip up a graph. I'm sure I got a poster for it somewhere that's not quite in the stack, so I'll just draw this one from scratch. Okay. You guys got a quiz question I know recently that looked like this. Right? If you're like compressing a spring, so here's like a force on Newton's third law equal and opposite force, so force, right? To compress a spring, suppose you compress it like some amount x, right? And then you make a graph. Force, say like in newtons, versus x, say in meters, right? What does that graph look like for compressing a spring? What does that graph look like? Hint. F equals kx. That's Hooke's law. Is that just a straight line? Right? Okay. So the more force you put on it, the more it compresses, in the compression example, right? Or it could be stretching in case of the spring scale. And that happens at a linear rate. So if it's like 3 times the force, it'd be like 3 times the compression. Right? Now that's Hooke's law, F equals kx. Right? Now, what does this graph have to do with like energy stored in the spring? 1/2 kx squared. Here's what property of that graph tells you how much energy stored in the spring. Well, I know the slope is like spring constant, right? F equals kx squared. Right? Hey, is it the area under the curve? Area under the curve? Right? That's like spring potential energy. I'll call it U sub s. Right? And then see if this is some general value x, and this is the resulting force, which is like kx, right? Isn't the area of a triangle 1/2 base height? Let's see what that is. U stored in the spring. Potential energy stored in the spring. That's what U is, right? Potential energy stored in the spring. Is 1/2 base height. So there's the base, there's the height, and oh, look at there. There's 1/2 kx squared. Just combine those x's, right? 1/2 kx squared, right? Stored in the spring. A little bit different way of looking at it, right? It takes more and more force to stretch it more and more, and it takes also more and more work, right? Right. And then energy of motion, 1/2 mv squared, right? So something has a mass and a speed, basically, right? Now these are all scalar values. So do I care about the direction of motion, whether it's going like up or to the side or down? In this section, no. And you can set up conservation of energy equations, and that could be an advantage or a disadvantage, right? You can whip off equations, solve stuff really fast, but you do lose directional information. So if you want that, maybe you have to solve it more like sines and cosines, projectile, which can take more paper, but maybe has more information embedded in it, right? This very last green row, don't worry about that until after Thanksgiving. That involves like the energy of like, say like a marble rolling down a hill or something like that. Okay. All right, so you guys good so far? How's that? All right. Okay, so we got work is force times distance. We're looking at that one. Okay. Here's a different perspective of the same thing. Hey, right, it's the area under the curve of the force versus distance, right? Whenever you open up the physics textbook and you see these axes against each other, force versus distance, there's a good chance that the question involved has something to do with how much energy was transferred, how much work was done, same thing, right? Now here I'm showing a constant force. So the area of that ends up being a very simple rectangle, right? But if it was a variable force, well, that could be just what I just drew, right? If it was like a variable force, right? It's still the area under the curve, represents how much energy or how much work, right? Okay. Same concept. Right. Okay, there was also power. So power is work per time. This poster is geared towards a unique situation of what if something's on the move? Like what if you're lifting an elevator, right? That could be this, right? Lifting an elevator. Right? Now here I'm showing the tension force. The tension in this cable is equivalent to the weight, right? Which implies that either it's at rest or it's constant velocity. So this particular elevator is not accelerating, right? Okay, so what happens with this over here? Where are we going to do this? Well, I know work is force times distance. We just talked about that. Right? It's all in the same direction. It's all up. So dot product down. Cosine of 0 degrees is just 1, so I don't have to worry about this. But hey, what if I rope these variables together? Distance over time. Oh, that's velocity, right? So what's the power about? Like, there's a motor at the top of the shaft, drawing some number of watts. It's pulling up this elevator at constant speed. How many watts? Oh, well, basically, what is the weight of the elevator? Because that's equivalent to the tension force, right? Times how fast it's pulling, right? Same thing, right? So that's a fun one to know. If the elevator was accelerating, then this would just be true at a particular instant. And any quiz question tomorrow probably won't even go quite that technical, but that's a good one to know, right? If you take physics in college, good chance you'll see something like that. Probably pull that and solve something, right? All right, conservation of energy. So energy is conserved in closed systems. Remember, you can't create energy, you can't destroy energy. You can transfer forms, maybe like potential to kinetic or something like that, right? Or if you have an open system, say if there's an external force acting on the system. My classic example is a car brakes to a stop. You're treating friction forces external to the car, right? So you have some initial energy, sum of energy initial, right? You can add or subtract some number of joules of work that are done, right? No, and some energy final. And most of them, do you guys remember that 3-page energy table I had? It's like 12 different examples, right? 10 of those 12 examples were this top example, closed systems, but there were a couple that involved like external forces. There's a car braking to a stop on there, okay? All right, so here's a really classic fundamental example. In fact, I do think that this is fundamental enough to appear on a quiz tomorrow. I think this would be a fair quiz question, right? There's something like Galileo drops a ball off a tower. How fast is it going to the bottom? I mean, you guys have seen this question. I wouldn't be surprised if you guys have seen this question at least a dozen times by this point in this class, right? You can solve this with conservation of energy. You say it's all potential at the top, MGH, right? I think you guys have probably applied that plenty of times. You could probably memorize that, right? I'm planning on taking all these posters down by tomorrow and keep it kind of fair with all my other, with all the other physics teachers. So we compare apples to apples, right? So MGH, you guys can memorize that. 1/2 mv squared, memorize that, right? Boom, boom. Right? I mean, you guys have applied that so many times in this class anyway. It's probably not an effort to memorize that, right? Equate those because energy is conserved, right? And then the speed at the bottom. I mean, how many times have you guys seen those two, right? Square root 2gh, right? That was also true for the pendulum. How fast the pendulum swing at the bottom? Well, to calculate the height change, it was all square root 2gh. You guys also saw that back in kinematic days, you could have used this third kinematic expression. We get you the same thing. Actually, I have a whole poster just for that too, but just to remind you guys, right? Sometimes there's multiple ways you can solve physics problems, and physics is all self-consistent. So solve it one way, solve the other way. Okay. Let's try. Actually, I think it's the next poster. Yeah, it's the next one. Right. This is just the reverse question. What if you throw a ball upwards and you want to know what's the maximum height that it goes to, right? So throw a ball upwards. Say you know you're throwing speed. I wonder how high does it go, right? Here's a kinematic approach. Here's the energy approach, right? So see with the kinematic, the way I throw and the way it's accelerating, gravity's pulling its opposite, so it's negative sign. X in this case, the displacement is the maximum height, right? And the energy setup, see, it's all kinetic here, it's all potential here. You can equate those, right? But no matter how you approach it, you'll get the exact same answer, right? The maximum height goes to based on throwing speed, works out like that, right? Or you could turn this around. Maybe you want to know, I wonder how fast I can throw. You throw a ball straight up, and you got a friend standing on like some balcony, and you take a meter stick and say, okay, well, it went up this high, you take some meter sticks, okay, I can figure out how high I can throw. I wonder how fast I threw in the first place. And that is this line, hey, square root 2gh. Same as the Galileo question, right? Square root 2gh. See that all over the place. There it is one more time. Right? Let's do an example. Maybe I wonder. Suppose you can throw at 30 meters per second. That's how fast you can throw a baseball. Right? How high can that baseball go? Right? What's the maximum height? Go ahead and solve that. They figured it out. What's the maximum height you can throw that ball? What's the maximum height? This may or may not be a question tomorrow, but if it was, I think that would be a fair question. What's the maximum height? Right, so, well, it showed you got here, the poster I'm covering shows two different ways to do it, but let's do the energy way because that's the theme of our poster. So I'll say sum of energy at ground level when you're throwing it is equal to sum of energy at when it reaches maximum height, right? Oh, and when you throw it, what expression can I use? 1/2 mv squared, right? And when it reaches maximum height, what is the energy term for that? mgh. We're talking about max, right? So there's no other type of energy. Right? Oh, I never gave you the mass of the ball. Is that okay? Do you need the mass of the ball? Cancels up. So let's plug in some numbers. I said you threw this thing, and that's V naught, right? At 30 meter per second. Right? If the canceling mass really trips you up, you could just make up a mass like 1 kilogram, something like that. And then I got 10 meter per second squared. I'm calling gravity, and I'm solving for what is the maximum height thrown. Right? 30 squared. That's like 900 divided by 2 is 90. I'm so sorry. 900 divided by this 10 would be 90. Okay, divided by 2 is like 45. So H max is 45 meters. I may have asked you guys this exact question a few months ago, right? Or maybe asked you the reverse. If you throw a ball, it goes up 45 meters. How fast do you throw it? Oh, it must have been 30 meters per second. Right? You can go either way with this question. Right, you guys good there? If you see something like that tomorrow, you can solve that. Okay. All right. Ooh, Block Spring Earth System. This one I like a lot because it involves 3 of the main forms of mechanical energy, all stacked into one example. This was one of the examples on your 3-page table. You guys remember 12 different examples? This was one of them, right? So I've got this mass, I'm going to press it against the spring, which is this stuff, okay? Right. Then I compress it this much, then let go, flies around this loop. Let's get rid of friction, like there's no friction, right? So maybe the question could be like, how fast is going at the top? So let's make up some numbers for this one. Here, I'll cover up the sort of like the setup there, see if you guys can solve this from scratch. Okay. Suppose I give you, here, pick up something on the fly here. I got a spring constant of, say 1,000 Newton per meter. Okay. Let's have the compression distance, how about 10 centimeters? So what would that be, like 0.10 meters in base SI units? Right? Could you guys convert? If I said 10 centimeters, you would know to put it in meters like that, right? 2 decimal places, right? So a little bit of a risk here. Don't know for sure this is going to make it around, but I guess we're going to find out if this even works, right? Guys, what's going to maximize the chances of this making it around? Should I pick something really heavy or something really light? If it's really heavy, you guys go, make it out there and this is your arm. If it's really light, more likely to make it around. How about this guy right here? Let's see, what is this guy? This says 20 grams. 20 grams, how many kilograms is that? 0.02 kilogram, right? Is 20 grams, it's the same thing. So that's this guy right here. I need to tell you the height of the loop. Let's say the height of the loop is, how about 30 centimeters? That should probably make it around. I don't know, I guess we're about to find out. 30 centimeters, how many meters is that? 0.30 meters, right? Oh, here's 30 centimeters right here. Good visual, right? Hey, is this a little bit less than a third of the meter stick? But if you had 3 of these, it'd be a little bit short of a meter stick. Right? And the question then is, how fast at the top? What's V top? That's the question, right? I hope those numbers work out. If they do, maybe I'll just use those numbers later today, but it'll fly. So you guys solve it, I'll solve it. Let's see if we all get the same answer. Okay. Yeah, it's gonna make it around. Ooh, yeah, it'll plenty make it around. All right. Yeah, those numbers work. All right, so I got an answer. I'm gonna run it one more time on my calculator to make sure I get the same thing. Looks like I made a mistake. All right, and I'll see if you guys got it. All right, who thinks they know the answer? How fast is it going at the top? Who thinks they know? Right, okay. All right, so let's start stepping through this. I need conservation of energy. So what's the source of all the energy? All the energy is initially in the spring, right? Let me do a setup here. Sum of energy initial equals sum of energy final. Okay? So I've got initial point, final point, right? Point A, point B. Let's grab that. And initially it was all in the spring. What's the expression for that? 1/2 kx squared, right? That's right? And then by the time it gets to the final location, now the energy is, I'm thinking 2 places it went. Where and where? I had to lift it against gravity. There's gravitational potential. What's the term for that? MGH. Right? And then I bet it had some energy left over. They all went to, and what should I write to finish this off? 1/2 mv squared, right? And we're solving for this V, right? Now nothing here cancels out, so we need all the numbers that I gave you. But you need to know the mass, otherwise different masses will work out different, right? So, I gave you, first of all, are you guys okay with that setup? Okay, great. Now let's look at the numbers. Okay. So I've got 1/2, got 1,000 Newton per meter. I compressed it 0.1 meters. If you like, that's 10 centimeters. Square that, 1/2 kx squared. It's just the x getting squared. Equals, here's that little tiny mass, kilograms. I'll call it G, 10 meters per second squared. If you want to use 9.8, then it's going to be multiple choice tomorrow, so the answers won't be like crazy different, right? And then height. I gave you guys a height change of 30 centimeters, so I'll call it 0.30 meters. Okay. And plus 1/2, 0.02 kilogram. And then V we're solving for squared. Boom. Okay, guys get that? Okay. Let's do some energy accounting. So 1/2 times 1,000 times 0.1 squared. Okay, this is like 5, guys, 5 what? That's 5 what? Joules, because energy, right? These are all energy terms. Joules, joules, joules. This is 0.02 times 10 times 0.3. Ooh, that's really small by comparison. 0.06 joules. Wow, right. So relative to the initial energy in the spring, not very much was needed to actually lift against gravity. Right? So almost everything's left over for those. Right? Maybe those numbers worked out a little bit too good, right? I think if you forgot those terms, probably something close enough for multiple choice, right? Okay, so this is like, well, half of that is like 0.01, I guess, right? I got a kilogram as a unit, and I got a V squared. Okay, so I'm gonna subtract this over. It's like 4.94. That's joules. It was 0.01, got a kilogram in the mix, and then V squared. Okay, divide this over. So it's like 494. Joules over kilogram, that's meters squared per second squared. That's equal to V squared. Square root both sides, 494 square root. Okay. That's V is at 22.2 meters per second. There you go. That's how fast it's going to go flying around. All right. You guys can do that setup. Okay. That might be like I think that would be a fair question. That would be probably the most complex type question that could be asked, right? But here, the premise is, right, that energy turns into that plus that, and you just plug stuff in and do some algebra. Right, you guys could handle something like that tomorrow. All right. Ooh, pendulum maximum speed. It's a good one to know. You guys did a whole lab on this type, right? Right. All right. So, okay. Remember, this quiz tomorrow has to be good for like conceptual students too. So this might be a little bit outside the bounds of the question, right? But here, let's go through this anyway, right? So, good classic question is, what's the speed of the pendulum at the bottom, right? And a good follow-up question to this goes back to like a few weeks ago. It's like, what's the tension in the string, right? Which is more than the weight of the object if this is motion. Think about centrifugal force stuff, right? But that's not on tomorrow quiz, so right, just a side thought there. Right? So how are you gonna figure out how fast it's going at the bottom? Right? Well, you can use up energy conservation. You say, well, it's all potential energy here and it's all kinetic energy here. MGH goes to 1/2 mv squared. Right? The mass of the object cancels out. Right? So different masses are going to have the same type motion side by side. Right? Notice in the final solution, there's no mass in here, right? Mass cancels out. Right? And then it actually ends up being like the same idea as the Galileo question. The speed at the bottom is square root 2gh, right? But this height change has some extra fun geometry tagged to it. What is this height change? In terms of the length of the pendulum and the starting angle from the vertical, right? Let's step through, how do you get that, right? Well, do you guys see a nice right triangle right here? Nice right triangle, right? And one of the first things we ever did in this class was like vector components, sine, cosine, right? This leg of this triangle is L cosine theta, isn't it? And this L and this L are the same L, right? Length of the pendulum is the same. Right? Therefore, this height change between these two dashed lines, end to end, is the difference between the full L of the pendulum and the L cosine theta. Well, that's that right there, L minus L cosine theta. Okay. If you like, you can factor the L out, looks like that, right? You can substitute that right up in here for H. That H got substitute. I did skip a few steps between here and here, right? But one of those steps I skipped is to substitute L1 minus cosine theta, and for this H, right? So square root 2gh is what it is. Square root 2g L1 minus cosine theta. You could add a spin on this. What if you push off? What if this is like a guy swinging on a vine? He doesn't start from rest, it pushes off, right? Well, that means that in an energy context, he had some initial kinetic energy. So in gray ink here, I put 1/2 mv squared, right? Now, how's that going to translate to the final answer? It ends up being that you can't do final speed equals initial speed plus the square root 2. No, that doesn't work out. You have to do final speed is equal to the square root of, and then the initial speed squared plus, blah, 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 right? Which gives you a different answer, right? So that's the correct way to do it, right? So that was pretty fun. You guys did this as one of your labs. I had you guys make a lab table look about like that. You guys calculated what ideally should the speed at the bottom be, right, based on this L and this theta. You guys have the protractor and the meter stick bottom. Right? And then you took those speed gates. You said, well, what actually was the speed at the bottom? So you had like two speeds, right? One calculated, one empirical measurement. And a lot of you guys got like same value, pretty close to. Right? Ooh, here's a really classic physics question. What's the minimum height of a roller coaster to make sure it gets around this loop? Right? I played you guys a video that was like there's like a bowling ball up here, right? Now the bowling ball was actually rotating itself, so there's a little bit of rotational dynamics. So kind of skip through that a little bit. Right? But what if it's like a car that has little tiny wheels on it? Right? And what if there was like no friction? Oh, look at that! Like no frictional losses. Right? No frictional losses. Right? What's the theoretical minimum height drop? Right? Now this involves two parts of physics you have to put together. Right? This is I wouldn't ask you to solve this whole thing from scratch on a quiz tomorrow. I don't think this would be a fair quiz question for tomorrow, right? Maybe part of this, possibly, right? But not the whole thing. But here's how you would do it. If you guys take physics in college, a science track, pretty good chance you're going to see this question in the future, right? So start with what we did like about a month back, which is this rotational, centripetal force stuff, right? So there is like a minimum speed that this cart has to have at the top of the loop, because if it runs into zero speed here, it's going to fall off the track, and that would be no good. So what is the minimum speed? It needs to be in square root GR. That comes from the centripetal force is provided only by its weight, right? And then the normal force from the track approaches zero in the minimum case, right? So if you look at like the tipping point case, it just barely gets around. I'll let the normal force from the track go to zero, right? And you get the speed, the minimum speed is square root GR. It's okay if it goes faster than that, but it can't go any slower, right? So what height drop is going to lead to at least that speed. And here's where the energy conservation kicks in. We're going to say at the top, it's all potential energy, MGH, right? But this H I'm playing off is relative to this floor way down here. Here's the ground way down here, which means by the time it gets to point B, well, it is also elevated. So it's got some potential energy there. There's your MGH, but this height is 2R. Right? Twice the radial size, right? Diameter of a circle, right? And then whatever's left over, and there better be some energy left over to go into kinetic energy, there's your 1/2 mv squared, right? 1/2 mv squared. And in place of v squared, there's your GR. So there's that substitution right there from a month ago physics, right? Just remember that. Centripetal force. Okay, and then you play this out. A bunch of stuff cancels, right? The mass of the cart cancels, doesn't make any difference. If you send down an empty cart or a cart full of passengers, makes no difference. The gravity field of the planet cancels out. If you took this whole system to the moon, you would get the exact same answer. And the answer at the end of the algebra ends up being 5/2 of the radius, so 2.5 times the radius. So if you count 1, 2, and then a half, so right about here, right about there. Right? That's like the theoretical minimum height. Right. Right. So that one's fun. A little bit complex there. Right. But if you could do this one from scratch, then you're definitely good for the quiz tomorrow, right? Because I definitely mastered this stuff. Right. Ooh, car brakes to a stop. All right. Okay. This one, a little bit of complexity here, right? So car brakes to a stop. I'm going to treat this as an open system. Say the car started with a bunch of kinetic energy, 1/2 mv squared, and it ends up with zero mechanical energy. So I'm just focused on the car, a system that consists of only the car, right? So where'd the energy go? Oh, it was pulled up by work done by friction. Work done by friction, which is force of friction times distance, right? I'm subtracting, right? Taking energy out of the system, or the distance and the friction force are opposite of each other. For both those reasons, I got a negative sign thrown in the mix, right? Now, what am I going to do with this friction force? Well, I'm going to do some substitutions here, right? So let's go back about 2 months ago. We're going way back in this class. Do you guys remember what is friction force relative to normal force? It's friction force is coefficient of friction times the normal force. So for example, if on this graphic, if friction force is half of the normal force, well, that means that the coefficient of friction is 1/2, right? There's different kinds of coefficient of friction. Let's not quite get into those details, but something like that. I told you guys about anti-lock braking, blah, 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 or minus square. So, what else do you know? I know that normal force is equivalent to the weight of the car, right? Ignoring the rotation of the Earth. I guess it's different by about 0.3%, but we're just going to ignore that, right? So there you go, right? So I made a double substitution right here. Friction force is coefficient of friction times normal force equivalent to the weight, boom, boom. This is like a double substitution, right? And usually the question is, what's the stopping distance? What's the braking distance? Say as a function of the initial speed of the car. right? That's usually the question given to you, right? And that could be answered by this right here, right? Alternatively, you could use this to solve for something else, like coefficient of friction. What if you know the initial speed of the car and you also measure the braking distance? You could calculate what is coefficient of friction, right? So you could do that too, right? And I think the most interesting relationship out of this, I thought it was so interesting, I pulled out, made its own proportionality here, is the braking distance. How's that proportional to the initial speed of the car? And that's a squared relationship, right? This is a point I made a few times, right? So like if you triple, let's see if you guys get this, right? If you triple the initial speed of the car, what happens to the braking distance? It increases how many times? Not 3 times. What's 3 squared? It's 9 times. 9 times the braking distance. If you want to turn this into a whole problem, test that out, and make a bunch of numbers, you could do that. But you'll always get 9 times the braking distance for 3 times the speed. Okay? How about this question? What if you triple the mass of the car? Right, so we had an empty car, right, and then it rolls by later, and it's like, oh, now it's a whole clown car. It's full of like all these clowns and groceries. All right, right. So 3 times the mass of the car, but all else equal, same tires, same speed. Right? What happens to the braking distance then? Is it the same as before? Yep, same as before, because the mass cancel it out. It doesn't actually matter how massive the car is. Ooh, that's another classic physics question. Notice mass doesn't actually appear in this equation down here at all. There's no mass. Well, I mean, mass is there, but it doesn't matter what the mass is. Okay. Ooh, Atwood. You guys have seen some Atwoods. Did we solve an Atwood with energy? Well, if we did or not, here's how you would set it up. Okay. So if you see an Atwood fall some distance, if you're specified the distance and you're asked like, how fast is it moving after some distance? The fastest way you can solve that particular question is energy conservation. You can say the supply of energy is the fact that the heavy block can fall, right? M2, GH, M2 is the heavier of the two, right? GH, right? And that H is like the falling height, right? And that energy goes into 3 different places. It has to lift the smaller block. So there's MGH lifting the smaller block. So there's one demand of the energy. Right? Also, it has to give each block a speed. That's like kinetic energy. So 1/2 mv squared for each block. I guess yeah, 3 places. Okay. And if you're given, say, the masses and the height of fall and the gravity field, you could solve for this V. And this would be the same V. I mean, one's going down, one's going up. You can factor that out. Right? You guys see how you could solve that? This is the setup for solving, right? Right. That's not the only way to solve this. You could also solve for the acceleration, and then go back to kinematic motion and say, well, some height change, like some displacement with some acceleration, and you could get the speed that way too. Okay? Notice what variable is not printed on this page, which is time. I did not say anything about time, right? Obviously, it takes some time for this process to happen also, right? But maybe that's a hint that you could use energy instead of that other process. If I said it felt like for like so many seconds, I probably actually would do that other process of like acceleration followed by kinematic motion. But if you see a height change, this is actually the faster way to solve it. Okay. Will you see this on tomorrow quiz? Probably not. Or if you saw something like this, it would probably be some like boiled down question of like, maybe this right here. I think this would be fair. It's like, what would the setup be? Like, could you at least get the setup? Right. All right. Here's another version of this. All right. So we got all right. Well, here. We move on a little bit faster. All right. All right. Simple machines. You can get some mechanical advantage. You can multiply your strength. Remember, you can't multiply the amount of energy in the system. You can't multiply the amount of work done, right? Other than, of course, maybe you can lift something that you couldn't before, but right. But you can amplify your strength, like the force in newtons. I had you guys rig up some pulley systems, right? Here I'm looking at a 3-to-1 mechanical advantage system, right? At least the ideal would be 3-to-1. That's based on the geometry, right? Distance compared to distance, right? You have to pull lots and lots of string just to lift it a little bit. That's how you're like paying for your increased strength. Right. Your actual mechanical advantage is the ratio of the forces, which might be 3-to-1 or might be a little bit less than that. Right. You guys did a whole, here's your guys' lab table. Right. You guys set up different setups. Right. You can get a mechanical advantage with the lever, like get some leverage. We didn't quite do that lab, but could do that. Right. If you can't lift a box, but you can somehow get it on wheels and you can like wheel it up an incline, here's mechanical advantage associated with that. Right. Here's how about a wheel, right? This is basically leverage, right? So if you have like turns into like a seesaw kind of lever thing, right? Same thing, right? You pull lots and lots of string to lift this up a little bit at a time, but you effectively amplify your strength, just the ratio of the rate of emphasis, right? All right, so this one's a little bit more technical, but did I show you guys how, I forget if I showed you guys just my AP classes, how the universal formula of potential energy can turn into MGH, right? Like go from the top of Mount Everest down to sea level. Did we do that one in class? No? Okay, maybe it was just AP, right? Anyway, right, so, right, so there's energy. Right, now let's switch over and do a review on momentum, right? Which if you're more familiar with, maybe fresh in your mind because we've been full focusing on this for the last couple of weeks. Okay? So momentum is mass times velocity. This is a vector value. All those energy that we were just looking at were all scalars, but momentum we're back to vectors. So direction is really important. Is it positive, negative? It's going right or left. Okay. You know, it's conserved just like energy was conserved in a closed system. Momentum was also conserved in the closed system. But don't forget, possible negative signs are back to being important, right? And it's involved in collisions. If you open up a physics textbook and you see some collisions going on, take in terms of this right here. Okay. So momentum being conserved. Oh, here's conservation of momentum right here. So for closed system, see, boom, something like that. You guys had some collision carts. How do you guys have, right? And I can say the momentum before the collision equals the momentum after the collision. If I add all the mass times velocity bits, mv, right, boom, boom, add them up before, the sum of, that means add them up, right? And then after the collision, boom, right, mv, add them up, right? It all has to equate. Now there's some information missing from this. We don't know exactly what kind of collision this is. These objects might even stick together, or maybe they're super elastic, like Newton's cradle, right? Or maybe it's like half deflated tennis balls. Regardless of what type of collision it is, this conservation always holds, right? But there could be like two unknowns. I don't know how much velocity for each one, like post collision. Right? Well, it depends on what type of collision, right? Okay. Don't forget, if they're going opposite directions, you have to include like a positive and a negative sign, right? Because vector values. Right? Right, so now let's get into what type of collision. At one extreme, at one boundary, you could have perfectly inelastic, which means they stick together. And the equation starts the same. You add up the mv bits before the collision. Okay? And then post collision, you have one giant mass moving at some common final velocity. That's it. This is the lab I had you guys do with the collision carts. I had you guys tape on some magnets and stuck together, right? Something like that. Right? Oh, and okay. So you guys go with that? The other extreme kind of condition you could have, collision, would be perfectly elastic. That's the exact opposite. That's like perfectly bouncy. And within reaching distance, that's probably as close as I can get in this class to like perfectly bouncy. But this collision carts you had with the magnets, they could bounce off each other pretty well too. Okay? Can you ever exactly achieve this? Maybe you can kind of approach it. And what makes this collision special in terms of physics is, okay, not only is momentum conserved, but this is true for all collisions anyway, right? But also kinetic energy is conserved, right? You set up a system of equations. This is the outcome of that. Now you guys do not have to memorize this at all for this class, especially for tomorrow, right? But if you take physics in college, there's a good chance that you'd be expected to solve that, and these notes could save a lot of time. There you go. Right, it's a crazy fraction. All right, so let's put it all on the table. Here's a new poster. Not that you guys seen this one yet. Right? So I got here. These first three rows are a spectrum of different types of collisions: perfectly bouncy, perfectly sticky, somewhere in the middle, right? And then for funsies, I threw on explosion, which is just like reverse inelastic collision. You guys remember the grenade question? Grenade explodes into different parts. Right? For every single one of these, momentum is always conserved. Right? Now, kinetic energy, there's a different story going on. If kinetic energy is also conserved, that's only perfectly bouncy. Right? If it decreases, well, in general, it'll decrease, and it has to decrease for perfectly inelastic. And I had you guys account that in your lab too. You guys saw that. Right? Kinetic energy will increase for an explosion or for like throwing a ball. Remember frictionless field? A pitcher throws the ball and gets kicked back the other way, right? Kinetic energy increase there. That energy comes from somewhere. In case of grenade, maybe from a chemical reaction. In case of throwing a ball, maybe from your muscles. Right. Right. Oh, how'd you guys do? Your lab, got lab tables going on. Right. How bouncy is a collision? The physics term for that is coefficient of restitution. And that means what is the post-collision difference of velocity compared to the pre-collision difference of velocity if I'm taking difference of velocities, right? Notice that mass is not part of this setup, right? But maybe material properties matter, right? And a version of this is like bouncing a ball off a floor. Oops, I have this one first. Right? Where the two objects colliding are like the ball and the earth, right? Now it does matter, again, material properties. If you bounce it off a tile floor versus a carpet floor, it'll make a difference, right? Where the earth is basically not moving either, but for this setup, right? So what's the difference in, what is the rebound speed compared to the crash speed? Because that ratio will tell you coefficient of restitution. Now this one, did you guys do this lab yesterday? Yesterday, I think it was. Right? Yeah, yesterday lab, right? You guys had meter sticks. You measured what is the rebound height compared to the drop height, right? Now that ratio itself is not coefficient of restitution, but you can use that to figure it out. Because oh hey, you guys remember Galileo dropping off the Leaning Tower? The crash speed was square root 2gh, right? And similar story for like rebound height and rebound speed, also square root 2gh, right? So take that ratio, the 2g cancels out, and ends up being the square root of the ratio of the heights. Will tell you coefficient of restitution. Okay, you guys figured that out. Okay. So yeah, here's your lab yesterday. Right? So you guys had that. You could probably navigate that, right? Okay. Okay. Impulse, right? Impulse. Last idea we're gonna look at. Impulse could be a transfer of momentum, right? Off of like an open system. Say you're looking at just like this ball here as an open system, right? That's force times time. Force times time will result in its own mass times change velocity. If you see a force versus time graph, the area under the graph tells you the transfer of momentum. Oftentimes, these graphs are like triangle shaped because like the force builds up and then releases, right? And oftentimes, these time intervals are very small, like fractions of a second. I got that too, right? A couple posters up here, right? How about if you fire a bullet at a bowling ball versus a bouncy ball, but let's say they start with the exact same momentum, mass times velocity is all the same, same. But the collisions are different. Guys, which gets this ball rolling faster, the inelastic or the elastic? Which one gets it rolling faster? The elastic. It transfers more momentum. So we stepped through that before. Got short time, right? Finally, ballistic pendulum. Now, I wouldn't expect you to solve this whole thing from scratch without any aid tomorrow on the quiz, but maybe you get the general principle, right? So there's a bullet fired, there's some momentum, there's a collision, pow, gets this block movement at some speed, which sends it up some height. Usually the question is, if you know what is this height change, can you back calculate what's the initial speed? Two parts. Conservation of energy to figure out what is the post-collision speed. Oh, square root 2gh. Hey, there's again. Right? And then the second part, what collision led to that in the first place? All the momentum came from the bullet, therefore you can solve for the initial speed of the bullet. Right? 2D collision, I don't think it's gonna be a question on that. All right, there you go. There is everything we've done in the last 4 weeks. All right, so you guys ready for this quiz tomorrow? Yeah, everybody's ready. All right, that's our wrap.